F, Wilhelm, Benjamin, are you there?
Yeah, I'm there, and I hope you can hear me.
I can indeed. Okay, so booth F, improvement of electric vehicle battery safety through simulation, tests, and advanced components, DEMOBASE. Wilhelm, Benjamin, the floor is yours.
Thank you very much for the introduction. I'm Wilhelm Maurer for Infineon Technologies, and I bring you first the thing that you read last in the title, the advanced components. And the major part of this presentation will be then done by INERIS on the safety simulations and tests. So let's start with how to improve safety by using advanced semiconductor components. Of course, you know Infineon is a semiconductor company, and this is our business. And one of the parts of this business has been to develop better and better switches. So here we are at the second generation of silicon MOSFETs for a battery management or battery main switch, a BMS. It's unfortunately the same acronym. We have used, as said here, a new superjunction MOSFET in an innovative topside cooling. This is a very special package that has been developed in this project for this purpose. And at the end, what you see here in the upper left is a conventional battery main switch and a prototype that we have built. Actually, we have built already a smaller one based on silicon carbide.
Are we looking at the same thing? I can only see the title slide.
Oh, I'm sorry. You should be able to see.
There we go.
Can you see it now? Yeah. Okay, so you don't get the projection. Okay. Thanks for pointing out. Yeah, as said, we have this innovative semiconductor switch, the MOSFET. And with this, we were able to produce a rather small and rather compact switch, which has the main advantage, and I think Philippe mentioned this already this morning, that it switches about 1,000 times faster than this mechanical switch, which means if you detect a short, either internal or external, you can switch off so fast that the battery doesn't get hurt, and especially the most sensitive cells if you have really very high energy densities. And as you can see here, this is switching off characteristics. It really works, and it works also under full load. And in this case, it was done for about 450 volts. But of course, there are many different options available. And the second thing that Infineon has been working in DEMOBASE was a cell pressure sensor. And the basic concept was you take a tire pressure sensor, modify it by making it more robust against the aggressive electrolyte in the cell. And then you just put it on top of the filling hole of a prismatic cell. And then, this is the cross section. And then you can measure the pressure in the cell directly. And we have found out in other projects that this is very helpful, especially as a second way of detecting dangerous things happening. So in order to provide this functional safety, this will be very helpful, I think, in the future. And what we have done here in DEMOBASE was working on this passivation layer. And you see here, what you have to do, you have to simulate and you have to find out better ways. And of course, the better ways work better. So at the very end for Infineon, there is a whole, how should I say, flower bouquet of different options in the product portfolio, which can help you in the battery management, like charging control, the pack monitoring, condition predictions, embedded functional safety features, overload protection switches, and also thermal management. And in this case, I hope I could show you a little glance on what is Infineon doing in this. And I hand over then to INERIS, to my colleague.
Okay, thank you very much. Benjamin, are you there?
Yes, I am.
Okay, please go ahead.
Wilhelm, you continue to switch slide, or do I have to do?
I will continue to switch slides.
Perfect, thank you.
I think Wilhelm's going to... going to switch the slides.
Perfect.
Yeah.
Good afternoon, everybody. My name is Benjamin Truchot. I'm working in INERIS, a French company, more especially involved in risk management in all the industrial fields. One of the role of INERIS in the DEMOBASE project was to work on the way to model the thermal runaway propagation inside a battery. To do that, we use several approaches using first experimental testing and next to CFD. The first step, as shown on this slide, was to provide a better understanding of the different phenomena that can occur during a thermal runaway at cell scale. We do a lot of tests using only one cell with different apparatus such as the arc calorimeter or overcharge testing or some other aggregation on the battery to understand the interaction between the different phenomena and to try to fix the way the heat release rate is governed by the ignition source. During those tests, if you can move the slide, please. Oh, thank you.
Next slide.
During this test, we also did a lot of measurements. We measured a lot of quantity at the cell level itself, as the voltage and so on. But we also tried to measure the different characteristics of the heat release rate and the gas emission. You can see, for example, on that slide, the emission rate for different gases, such as carbon oxides or total hydrocarbon produced by the event. And during some of the tests, we also try measuring the characteristic of the fire, not only in terms of heat release rate, but also in terms of temperature or thermal radiation, because this part at cell level, as shown on that slide, is exactly the input of our model. The objective of the global model consists in using the data at cell scale and to make a model that take into account all the physical phenomena we know about the battery and try to evaluating the global heat release rate for the battery. To do that, from the cell behavior itself, having in mind the different phenomena that occur, we go to the module thermal runaway modeling. To predict the module behavior, it is important to first take into account the cell behavior itself, the gas release behavior outside the cell when the electrolyte will start burning in the air, the associated radiation, because this radiation will hit the surrounding cells, but although, and this is a very important point, the conduction through the solid. And this conduction, although enabled to take into account insulation barriers that can be designed for a reduced thermal runaway propagation velocity. At this scale, it is enabled to use, I will show that later, some experimental tests to validate the model. And at the end, using the cell-to-cell interaction and the module-to-module interaction, it is possible to model the full battery thermal runaway propagation. This is quite complex because on top of the radiation effect, the combustion behavior and the conduction through the solid, the gas combustion is also governed by the behavior of the casing of the battery. And depending on the opening of the event, for example, the oxygen inside the casing will varies and consequently varies the fire behavior. So next, this is an example of what we did. We use an open CFD code, which is FireFoam. This is a well-known code in the field of fire safety. It is based on the OpenFoam general code and is especially dedicated to fire modeling. This code enables to take into account the different characteristics of the fire, mainly the fuel characteristic and the specific heat release rate. Then we first try burning a cell by this code, just reproducing the fire test we did in the lab. Then we module first a group of 3 cells. We also did that in the lab and tried to model the thermal runaway propagation by taking into account both the thermal conduction in the one-dimensional from one cell to the other, and although the 3D fire modeling as shown on the picture with the different thermal fluxes applied on the different surface of the sample. Of course, to do that, we did not go into the detail of the chemistry inside the cell. We consider that the runaway starts when the temperature inside the electrolyte reach 120 degrees. This step next enables us to introduce such a curve inside the battery geometry. And next, this is the experimental validation step with the cluster scale. This is what you can see on this picture. This is a cluster of 3 cells, and we did on that cluster different experimental tests to get some data to validate the model. For those tests, we measure the same quantities that we did for the cell scale level, typically the heat release rate, because this is a value we used for validating the code, but although the thermal radiations, temperatures, and the nature of the released gas. On the first comparison, we did show that the model is in quite good agreement with the experiment, having in mind that the heat release rate from a cluster could vary depending on the situation of the aggregation. And the objective is to be able providing a safe approach. And then, to conclude, we want to give some acknowledgement regarding this work through the DEMOBASE project and its coordinator, Mr. Depré. And you can show on that slide the different partners of the project. So thank you for your attention.
Thank you very much. I have a question. How many megajoules of heat did you get from that battery on the previous slide? Slide 12. Wilhelm, if you can go back one slide. That's it. Total heat of combustion, 1 megajoule.
1.13 megajoule.
Maybe we should just burn batteries instead of petrol.
But inside the battery, you have some electrolyte, which is a carbonated materials. It burns very well.
So that's the range extender then. We burn the battery.
Yeah.
Okay. If you have any questions, people put them into the chat. What about the synergy between testing and simulation? You've tested to destruction. You have models. Do you measure what you predicted? Can you predict what you measured? How far away are they?
The objective of this coupled approach is to be able to do a lot of prediction using the simulation. At the present situation, honestly, the test is still required to validate the model and to understand a certain type of phenomena because of the complexity of the chemistry inside the cell and the complexity of the propagation. But the objective is to be able, using small-scale test, to qualify the cell, and next to use the simulation to predict the behavior at the module or the battery scale without doing a lot of tests that could be very expensive. Typically, if you want to design safety measures for the battery, it is quite easy to do that with the simulation by introducing some installation plates, some different characteristics of the event, to change some geometrical aspect of the battery. And then you can do the final validation test for the battery, but all the design will be managed using the simulation.
But I understood from what you just said, you're not there yet. You're working on the simulation, it's good, but you're not there yet. Is that correct?
For the moment, it's quite difficult because there is a different situation that can occur at the cell level. We are quite able to predict the worst situation, but it's difficult to predict whether this worst situation will occur or not, because this is a strong coupling because the chemistry inside the cell itself and what happened outside.
So that's the good news.
Typically,
more research is required.
I'm sorry?
So that's the good news. More research is required.
Yes.
Okay, that's the good news. Well, thank you very much for your contribution, Wilhelm, Benjamin. Thank you.